Okay, welcome everyone. Today I'm going to be discussing the solutions to the 2020 AMC 8, and I think the idea here is I'll just go through each problem, discuss how I would have solved the problem, and generally like the thought process behind the problem, and then at any point if anyone has any questions, just unmute and let me know. So start with problem 1. Luca is making lemonade to sell at a school fundraiser. His recipe requires 4 times as much water as sugar and twice as much sugar as lemon juice. He uses 3 cups of lemon juice. How many cups of water does he need? So we're given that he needs 3 cups of lemon juice, and since he needs twice as much sugar, that means he needs 6 cups of sugar, and since he requires 4 times as much water as sugar, we multiply the 6 by 4, and we get 24. So our first answer is E. Problem 2. 4 friends do yard work for their neighbors over the weekend, earning $50, $20, $25, and $40 respectively. They decide to split their earnings equally among themselves, and we want to know in total how much the friend who earned $40 will give to the others. So if they're going to split this equally, we're essentially going to be finding the average of how much they made. So we take 15 plus 20 plus 25 and 40. And that's going to give us the total earnings, which is $100. And since we have 4 people here, the amount that they each get is going to be 100 over 4. 100 divided by 4. And that's going to be equal to $25. Oh boy. Okay. $25. And so the person who made $40 is only going to have $25 at the end, which means that they gave away $15. Problem 3. Carrie has a rectangular garden that measures 6 by 8 feet. She plants the entire garden with strawberry plants, and she's able to plant 4 strawberry plants per square foot, and she harvests 10 strawberries per plant. We want to know how many strawberries she can expect to harvest. So in her rectangular garden, it's 6 by 8 feet, so the area is going to be 48 square feet. And since each of those square feet can have 4 strawberry plants, we're going to multiply that by 4, and then since each strawberry plant has 10 strawberries, we multiply that by 10. And that gives us 1,920. So our answer is D. Problem 4. 3 hexagons of increasing size are shown below. Suppose the dot pattern continues so that each successive hexagon contains 1 more band of dots. How many dots are on the next hexagon? So in this one, it sort of makes sense to look at them by row. The first one just has 1 dot. Next we have rows of 2, 3, and then 2. And the next one we have rows of 3, 4, 5, 4, 3. So in each hexagon we have 2 more rows than the previous hexagon, and we also start with 1 more before 1 more dot in the first row. So in the next hexagon we'll expect to have 4, 5, 6, 7, 6, 5, and then 4. And so all we have to do is just add these up, and we will get the answer of 37. Problem 5. 3/4 of a pitcher is filled with pineapple juice. The pitcher is emptied by pouring an equal amount of juice into each of 5 cups. We want to know what percent of the total capacity of the pitcher each cup received. So we're told that we start with 3/4 of the pitcher, which if we convert that to a fraction with denominator 100 by multiplying by 25 on the top and bottom, we get that that's 75 divided by 100. The reason we want to do this is because the problem asks for and answer in percent, so a denominator of 100 is just very helpful here. Next, we're going to pour an equal amount into 5 cups, so each cup gets this much divided by 5. So 75% divided by 5, the 5s, is going to be equal to 15. And so that means that each cup gets 15% of the total capacity of the pitcher. Okay, next we have Aaron, Darren, Karen, Marin, and Sharon. We're riding on a small train with 5 cars that have 1 person in each seat. We're told that Marin sits in the last car, so I'll probably want to draw a diagram here. Put Marin in the last car. We're told that Aaron sits directly behind Sharon, so on our paper we'll probably want to make a small note of that. This was a bad idea. Okay. Here's Aaron, who sits directly behind Sharon. And then we're told that Darren sits in front of Aaron. But we also know that Sharon is sitting directly in front of Aaron, so Darren must sit even further in front somewhere. And then we're also told that at least 1 person sat between Karen and Darren. So Karen could either sit next to Darren, but we're told that that's not possible, or they could sit behind Aaron. So that's the only last spot for Karen. So we know that the final result must follow that exact format that we've found. And we're asked who sat in the middle car, and that would be Aaron. Problem 7. How many integers between 2020 and 2400 have 4 distinct digits, that means different, and are also arranged in increasing order? For example, 2, 3, 4, 7. So since both of the numbers at the endpoints of our range start with 2, every number that works must also start with 2. Next, we are going to look at the hundreds digit. Since we started with a 2, the hundreds digit must be at least 3. And it also cannot be 4, because then it would be bigger than 2400. So we know the hundreds digit must be a 3. So now we just have 2 digits to worry about. So all the possibilities for the tens digit would be 4 through 9. So we can make a list on the side here. 4, 5, 6, 7, 8, and 9. And then we'll look at how many possibilities there are for the ones digit for each of the possible tens digits. For 4, the ones digit could be anywhere from 5 through 9. And that gives us 5 possibilities. For 5, it could be anywhere from 6 through 9, so that would give us 4 possibilities. And the same pattern will keep going. For each increase in the tens digit, we lose 1 possible ones digit. So for 6, it would only be 7 through 9, giving us 3 possibilities, and then 2, 1, and 0. Because if the tens digit is 9, there's nothing bigger for the ones digit. So all we do is add up all of these numbers on the right side here, 1 through 5, and that gives us 15. Problem 8. Ricardo has 20 coins, some of which are pennies, 1-cent coins, and the rest of which are nickels, 5-cent coins. He has at least 1 penny and at least 1 nickel. We want to know the difference in cents between the greatest and least possible amounts of money. So the greatest possible amount of money would be maximizing the number of 5-cent coins. So we're going to want 2019 times 5 plus just 1 penny, which is just 1 cent. And the smallest possible would be the flip case of that. 2019 pennies, so 2019 times 1, plus a single nickel worth 5 cents. And what we want to do is find the difference between these. I'll put parentheses here. So 2019 times 5 minus 2019 times 1 That would give us 2019 times 4, and 1 minus 5 would give us just minus 4. So 2019 times 4 minus 4 is 2018 times 4, and that gives us an answer of C, 8072. Akasha's birthday cake is in the form of a 4x4x4-inch cube. The cake has icing on the top and the 4 side faces, but no icing on the bottom. Suppose the cake is cut into 64 smaller cubes, each 1x1x1 inch, as shown below. We want to know how many of the small pieces will have icing on exactly 2 sides. So in general, the edges are going to have icing on 2 sides. The corners will have icing on 3 sides, 1, 2, and 3, and the sort of like central squares will have icing on just 1 side. And so, except for the bottom, this will hold. On the bottom, the corners are going to be the pieces with only 2 sides frosted, and there are 4 corners on the bottom. And then, other than that, we're looking for how many edge pieces there are. So there's 1 here, 2 here, and you can see that there will be 4 such of these column style edge pieces. That adds another 8. And then there will also be 8 edges on the top face. And that adds up to 20 pieces. Answer is D. Problem 10. Zara has a collection of 4 marbles. I'm not going to try to pronounce that. Aggie, a bumblebee, a steely, and a tiger. She wants to display them on a row on a shelf, but does not want to put the steely and the tiger next to one another. In how many ways can she do this? So it's going to be a little bit annoying to try to list out all of the different orders that don't have them next to each other. It's actually going to be easier to put them next to each other and consider that to be the opposite of what we want, right? So in total, we have basically our strategy for this problem is going to take the total and consider this to be the total, and then we have the ones that work and the ones that don't work. We want to calculate the ones that work, where the steely and the tiger are not next to each other. However, it's a bit hard to calculate this. Rather, it's going to be easier to calculate the total and then subtract the cases that don't work. Each of those are easier to calculate than the successful cases on their own. So that's going to be our strategy here. So for the total, we're going to see how many orders there are without any restrictions. That would give us 4 choices for the first marble, 3 for the second, 2 for the next, and 1 for the last. Since 1 marble gets used in each spot, there's 1 less choice for the next. So the total here is what we get by multiplying all of these, which is 24. But now we have to subtract all the unsuccessful cases. The idea here is going to be, imagine taping the steely and the tiger together so that they make 1 new big marble that's actually 2. But anywhere you place this, it's going to be a failed case because they're right next to each other. So now what we effectively have is 3 marbles, and no matter how we order them, this is going to be a failed case. So there are 3 choices for the first, 2 for the second, and 1 for the last. And that gives us 6 scenarios here. However, when we place the steely and tiger marble, that can go in 2 different orders because the steely can be on the left or the tiger can be on the left. So we actually have to multiply this by 2, and that gives us 12 failed cases. And subtracting that from our total of 24, we have 12 successful cases. Problem 11. After school, Maya and Naomi headed to the beach 6 miles away. Maya decided to bike while Naomi took a bus. The graph shows their journeys, indicating the time and distance traveled, and we want the difference in miles per hour between their average speeds. So to find their average speeds, we're going to do distance over time. So Naomi, it looks like, is going to travel 6 miles in 10 minutes, which is 1/6 of an hour. So that's our denominator. It's going to be in miles per hour, and that gives us 36 for Naomi's average miles per hour. Maya travels the 6 miles, reaching the top here, in 30 minutes, which means that she took half an hour. So we're going to do 6 divided by a half, and that gives us 12. So we're asked for the difference between these two, which is just 24. For a positive integer n, the factorial notation n factorial represents the product of the integers from n to 1. For example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. What value of n satisfies the following equation? 5 factorial times 9 factorial equals 12 times n factorial. So what we're going to do here is find the prime factorization of each side so that we can find this n. However, we can use a bit of a shortcut here. We see that 5 factorial is going to have a factor of 5. We also see that 9 factorial is going to have a factor of 5 because 9 all the way down to 1 includes 5 when it gets multiplied. So there's going to be 2 factors of 5 on the left side. On the right side, the 12 has no factors of 5, so which means that n factorial must provide exactly 2 factors of 5. So that means that n must be at least 10, because 10 factorial has a 10, and then down to a 5, down to 1, that has 2 factors of 5. However, it also has to be less than 15, because that would introduce a third factor of 5. However, the left side has no factor of 11, yet any factorial of a number bigger than 10 would have a factor of 11. So that means that n is actually exactly 10. So we have a bit of a shortcut to save some time on this problem. Problem 13. Jamal has a drawer containing 6 green socks, 18 purple, and 12 orange. After adding more purple socks, he noticed that there is now a 60% chance that a random sock is purple. We want to know how many purple socks were added. So looking at the problem, we see that there's 18 socks that are non-purple. So 18 non-purple. Non-purple. And that's going to constitute 40% of the total socks. And from this ratio, we find that 45 socks constitutes 100% of the total socks. And also that there are 27 purples. And since we started with 18 purple socks, the difference between 18 and 27 is our answer, which is 9. And for anyone who's wondering about this step, going from 18 non-purple being 40% to a total of 45, that's multiplying 40% by 2.5. And if we're going to do that, we also have to multiply by 2.5 on the left side as well. And that keeps the equality, and we get 45 there. Okay, problem 14. There are 20 cities in the county of Newton. Their populations are shown in the bar chart, but we also have a line showing the average population. We want to know the number that is closest to the total population of all the cities. So we could try to estimate, the sum of all of these bars, but this average number is going to be very helpful because it means that the total number of people is very close to 20 times, whatever this number is. We're just going to estimate here. So halfway between 4,000 and 6,000 would be 5,000. I'll write 5K. And then right here, we would expect that to be 4,500. So this is really close to 4,750, I would say. And now doing this calculation out, you'll get 95,000. And that is our answer. So Suppose 15% of x equals 20% of y. We want to know what percentage of x is y. So we have 15% of x, which is 3 over 20 times x equals 4 over 20. Or actually, that's just 1 over 5, right? So what I've done is I've just simplified these percentages down to the simplest fraction. And now what we're going to do is remove these denominators by multiplying by 20 on both sides. So then what we get is that 3x equals 4y. What percentage of x is y? So that tells us we want to look for y divided by x. And dividing by x on both sides, as well as 4 on both sides, we get y over x equals 3 over 4, which is 75%. There's our answer. Problem 16. Each of the points A through F represents a different digit 1 through 6, and each of the 5 lines passes through some of these points. The digits are added to produce 5 sums, 1 for each line, and the total of all of them is 47. We want to find the digit represented by B. So if we look at the point A, there are 2 lines passing through it, so that means that the value of A is represented twice in the sum of 47. That's just an example for A. But if we try that for all of the other ones, we'll find that every letter is represented twice in the sum, except for B, which is represented 3 times. So what we're basically looking at is 47 equals 2 times, let's just say x, which basically represents the sum of A through F, because each of the letters is counted twice. But since B was counted 3 times, we're basically adding an additional B. And so this x here represents the sum of all the letters, and since the letters are 1 through 6, that's just 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21. And 2 times 21 is 42, so the digit we're looking for, B, is then 5. Problem 17. How many factors of 2020 have more than 3 factors? As an example, 12 has 6 factors, and they're listed. So the first thing we're going to want to do is find the prime factorization of 2020. We can see that's divisible by 10, as well as 2 because it's even. So immediately we'll start off by dividing by 10, by removing a 0 there. And after that, it's still even. So we can divide out another 2. And that leaves us with a 101. The 10 can be broken down further into 2 times 5. Everything here is prime, so we found the prime factorization. So for a number to have more than 3 factors, we need a number that is 1 prime times another prime, or 3 numbers multiplied, or 3 primes multiplied together. 2 of the same prime multiplied together results in a square number that only has 3 factors, so that does not qualify. So the numbers we're going to be looking for are 2 times 5, 5 times 101, 2 times 101. So these are all the possibilities for just 2 primes multiplied together. There are no other ones other than these. Next, we'll look for the ones that have 3 different, not necessarily different, but just 3 primes in their prime factorization. And of those, there is 2 times 5, 5, 2 times 2 times 101, 2 times 5 times 101. And finally we have 2020 itself, which is 2 times 2 times 5 times 101. And that's all the possibilities, so we have 7. Problem 18. Rectangle ABCD is inscribed inside a semicircle with diameter FE as shown in the figure. Given all these different side lengths, we want to find the area of the rectangle. So given a semicircle, it seems pretty natural to draw that center point, and that will split AD into 2 segments of length 8. So if this is 8, then we can see the radius of the circle from this center point. Let's call it O. OE is going to be 8 plus 9, which is 17. And because it's a semicircle, that 17 is the same distance from C to O as well. Pretend that's a straight line. Okay, here's 17. And this is also 8. And right here we have a right angle. So we have ODC, which is a right triangle. One of the legs is 8. The hypotenuse is 17. So we want to use the Pythagorean Theorem here to find the height. Because once we have the height, we can just use base times height to find the area of this rectangle, right? So what we have here is 8 squared plus CD squared. And that's going to be equal to 17 squared. That's by the Pythagorean Theorem. If you do out this math, you'll get that CD equals 15. And now we're almost done, because 15 times 16 gives us the answer 240. Okay, problem 19. A number is called flippy if its digits alternate between 2 distinct digits. For example, 2020 and 37373 are flippy, but these next two are not, right? We want to know how many 5-digit flippy numbers are divisible by 15. So 5 digits, 2, 3, 4, 5. So first, 15 is 3 times 5, so we need to satisfy both of these conditions separately. For 5, that's going to be the more restrictive one. It means we must end in a 0 or a 5. Now think about if we end in 0, then the hundreds digit has to be 0, and the 10,000s digit also has to be 0. But that doesn't work because a 5-digit number can't start with 0, otherwise it would become 4 digits, right? So that means we must end in 5, and based on the rule of a flippy number, that fills in these other digits. So now we just have to figure out what digit is these next two. And that's where this divisible by 3 comes in. We know that the sum of the digits has to be a multiple of 3. Now the first 3 5s here add up to 15, which is already a multiple of 3. So that means that these two digits must add up to a multiple of 3. And since they're actually they have to be the same digit, that means they also have to be divisible by 3 themselves. Otherwise, this won't work. So our choices are 0, 3, 6, or 9. And you can test for yourself that non-multiple of 3 will not work. And that's because multiplying by 2, that's not going to add a factor of 3, because that's how prime factorizations work. Each number has a unique prime factorization. So that means that there are only going to be 4 possibilities for flippy numbers that are also 5 digits. Problem 20. A scientist walking through a forest recorded as integers the heights of 5 trees, and each tree was either twice as tall or half as tall as the one to its right. Unfortunately, some data was lost, and basically there are now some blanks. Based on our observations, the scientist was able to reconstruct the data. We want to know the average height of the trees. So since the average height ends in 0.2, when we multiply it by 5, the number of trees to get the total, we're going to get something that is 1 more than a multiple of 5. Because this 0.2 times 5 is 1. This 11 also has a 1 more than a multiple of 5, so that means that the other 4 numbers have to add up to a multiple of 5. From here, it's trial and error. If you wanted to try 5.5 for the first one and 5.5 for the second one, you could, but that's not going to work. In reality, what is going to work is 22, 22, 44, and then 22. There's not too much to this problem, just trial and error mostly, but once you add these all up and divide by 5, you will get the answer of B, 24.2. Problem 21. We have a game board of 64 squares, and we're going to start from P and try to end at Q, making only these diagonal moves. One example is shown below. And we want to know how many possible paths there are. So obviously we can't go off the board, but we also can't really go too far out, otherwise we won't be able to make it back to Q. So we sort of see this square as far out as we can go before not being able to make it back to Q. So the way I would do this problem is by writing how many ways there are to get to each square. So to get here, there's just one. There's also one, 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 one. And that's just because it's the only way to get there is just by keep making left and up moves. Now to get to this square, it's a little more interesting. It's basically the number of ways to get to the one that's down and to the left and down and to the right, because from either of those squares you could get to this square. So this is just the sum of these two, which is 2. And we apply the same process going up, and this 3 to this square. It's the only way to get to that square, so it's the same number, right? Now from this one, we could keep going left, but then we won't make it to Q, so we need to start going back and repeating this process until we get to the top. So that gives us Q to be 28. 28 ways to get to Q. Problem number 22. We have a number, or a machine that basically takes a number and outputs another number based on whether n is even or odd. It'll have the number if it's even, or triple it and add 1 otherwise. And we see that we want to put n in 1, 2, 3, 4, 5, 6 times and get 1. And we want to know how many different ways there are to do this. So this step must be 2 because no odd number tripled at 1 would give you 1. That's also true for 2, so we must have had twice of 2 before, which is 4. Now we could have had 8, or we could have had 1. Both of these would have given you 4. And for the next step, 8 would have only come from 16, and 1 only comes from 2, which only comes from 4. 16 actually comes from 2 different numbers, 5 or 32. 32 only comes from 64. 5 only comes from 10. 4 comes from 8 or 1. So now all we have to do is just add these numbers together, and we'll have our answer, which is E. Okay. Problem 23. We have 5 awards to be given to 3 students. Each student receives at least 1 award. And how many ways can they be distributed? So we're going to start with the total ways to do this, which is 3 to the power of 5. That would just be for each award picking 1 student in any way. But now we have to subtract the cases where like 1 student doesn't get any awards. So I would be picking 2 of the students for each of the 5 awards. But we could have left out any student, so there's 3 ways to sort of do that. And each of these cases also includes a case where 1 student gets all the awards. So we sort of want to add that back in because we've subtracted that 3 times unnecessarily. So we need to add that back in. And we get the answer 240. This problem's a little bit complicated. This uses something called principle of inclusion and exclusion, which you can look up on AOPS after this. A large square region is paved with n squared gray tiles, each measuring s inches on a side, and we also have a border of d inches surrounding each tile. When there are 24 tiles per side, the tiles cover 64% of the area. We want to know the ratio d over s for this larger value n. So let's suppose each tile has side length 1, then if the tiles cover 64% of the area, the side lengths of the tiles cover the square root of this for just one side, and that's 80%. Let's see, 80%, because that squared gives you the 64%. So the side lengths of the tiles are 24 in total, and that means that the total side length had to be 30. So this extra length of 6, 30 minus 24, was equal to how many of these borders? Well, 25. There are 23 between the tiles and 1 extra on each side. So that was equal to 25 times this border. So that means that d is 6 divided by 25. Since s is just 1, the ratio d to s is also 6 over 25. Okay, we have 3 squares and 2 rectangles that combine to form this rectangle that is 3322 units wide and 2020 units high. We want the side length of S2. So let's call the side length of the square as S, the side lengths of the rectangle small r and big R. You know, small r plus S equals 2020. Big R plus S equals 3322. And for the side length of the small square, we have big R minus S. That's for this one. That's also equal to S minus small r. Rearranging this, we have 2S equals R plus R. And now what we want to do is what? Let's see. We're going to add these first two equations to get 3s on the left side, s, r plus r. That's actually 2s, so we have 4s on the left side, my bad. And that's equal to the sum of these, which is 5, 3, 4, 2. That gives us s equals 1335.5. I know the meeting's about to end, so if it ends, you can just rejoin. I'll start the meeting again. And yeah. So now we have the value of the big side length, and what we want to do is plug that back into one of these first two equations, because that gives us small r equals 684.5. And now what we can do is solve for s minus r, which is this side length here, right? That gives us 651. If anyone has any questions, just rejoin the meeting once it cuts us off. I know I rushed a little bit for these last questions, mostly because we're running out of time, but